What specific problem does the proposed method aim to solve?
The proposed method aims to solve the problem of understanding why transformer-based language models exhibit hierarchical generalization despite being trained on ambiguous data. The method investigates the influence of the training objective on hierarchical generalization in transformers and explores the preference for hierarchical structure over linear rules. It aims to explain the source of inductive bias for hierarchical generalization in transformers by comparing the simplicity and goodness of fit of hierarchical and linear grammars using a Bayesian framework. The method also aims to discover subnetworks within the trained models that correspond to different generalization behaviors, hierarchical and linear rules, and analyze how these subnetworks evolve during training. Ultimately, the method seeks to provide insights into the mechanisms behind hierarchical generalization in language models and understand the factors influencing their learning behavior.
How does the proposed method work? Illustrate step by step.
The proposed method works by first constructing probabilistic generative grammars, specifically context-free grammars, CFG, and regular grammars, to model the hierarchical and linear rules for a given task, such as simple agreement. These grammars are then used to generate datasets that are consistent with both rules, as well as datasets that are unique to each rule. The training dataset is constructed by considering the sentence types common between the CFG and regular grammar datasets. The posterior probabilities of these grammars are computed given the training datasets, balancing the goodness of fit and simplicity. The transformer-based language models are then trained on these datasets and evaluated on test sets corresponding to hierarchical and linear generalizations. The negative log, likelihood, NLL, and main verb accuracy are used to assess the model's preference for hierarchical or linear generalization. The results show that when the hierarchical grammar fits the data well and is simpler compared to the regular grammar, the transformer model exhibits hierarchical generalization. Conversely, when the one-state grammar fits the data best, indicating simplicity, the transformer model shows no preference for hierarchical generalization. Sensitivity analysis is conducted to explore the impact of varying the prior distribution parameter. The study provides insights into how transformers generalize hierarchically and the role of simplicity bias in this process.
What are the theoretical or practical benefits of using this method?
The theoretical benefits of using the method described in the paper include gaining insights into the hierarchical generalization behavior of transformer-based language models. By leveraging Bayesian framework and probabilistic grammars, the method helps in understanding why transformers exhibit hierarchical generalization despite being trained on ambiguous data. It provides a systematic approach to quantify the simplicity of competing hypotheses, hierarchical and linear rules, and explains the preference of transformer models towards hierarchical generalization. The method also sheds light on the internal mechanisms of transformer models and how they implement hierarchical structure during training. Practically, this method can be valuable for improving the training of transformer-based language models. By identifying the inductive bias towards hierarchical generalization, it can guide the development of more efficient and effective training strategies for transformers. Understanding the factors influencing hierarchical generalization can lead to better model performance in tasks requiring hierarchical structure understanding, such as question formation and tense reinflection. Additionally, the method can aid in designing more interpretable and explainable transformer models by uncovering subnetworks corresponding to different generalization behaviors. Overall, the method offers a structured approach to analyze and enhance the hierarchical generalization capabilities of transformer models, which can have implications for various natural language processing applications.
How is the method validated or tested?
The method is validated or tested by constructing probabilistic generative grammars, PCFGs, to model the data generation process for the hierarchical and linear rules. These grammars are used to generate datasets that are consistent with each rule. The likelihood and prior probabilities of the grammars are computed based on the training datasets. The posterior probabilities of the grammars are then calculated given the observed data. The grammars are compared based on their posterior probabilities to determine which grammar better balances the trade-off between goodness of fit and simplicity. The transformer-based language models are trained on these datasets and evaluated on test sets derived from the hierarchical and linear rules. The negative log, likelihood, NLL, and main verb accuracy are computed to assess the generalization behavior of the models. The models are compared to see if they exhibit a preference for hierarchical generalization based on the simpler grammar with higher posterior probability. Sensitivity analysis is also conducted by varying the parameter values of the geometric distribution to ensure the robustness of the results. The results show that the models trained on datasets consistent with the hierarchical rule exhibit hierarchical generalization, while those trained on datasets consistent with the linear rule do not show a preference for either rule, confirming the validity of the method.
What results were achieved with this new method?
The new method achieved results that showed transformers trained on data consistent with the hierarchical rule exhibited hierarchical generalization. Specifically, when trained on a dataset where the hierarchical grammar was simpler and fit the data better than the regular grammar with linear agreements, the transformers learned to generalize hierarchically. This was evidenced by the lower negative log, likelihood, NLL, values on the test sets corresponding to the hierarchical rule compared to the linear rule. The models trained on the dataset favoring the hierarchical rule obtained close to 100% accuracy on the hierarchical generalization test set, while the models trained on the dataset with no clear preference for hierarchical or linear rules obtained around 50% generalization accuracy, indicating no bias towards hierarchical generalization. Additionally, the study showed that the simplicity of the hierarchical grammar compared to the regular grammar influenced the transformers to generalize hierarchically, supporting the idea of a simplicity bias in the training setup.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method presented in the paper include the subjective nature of choosing the prior probabilities for the grammars, which can influence the results. Additionally, the study treats transformers as black boxes and does not provide insights into how these models internally implement hierarchical structure. The results obtained from the hand-constructed grammars may not be optimal, as there could exist better grammars in terms of posterior probabilities on the training datasets. The study also does not address the mechanistic explanations of why transformers exhibit hierarchical generalization. Furthermore, the method relies on an idealized setup and may not fully capture the complexities of real-world language acquisition and neural network behavior.